So people, can you hear me? Guys. People in the, okay, I think, guys, please. Okay, we'll just wait like 10 more seconds so that I can get that. So please, once you hear my voice, please confirm whether you can hear me or not. Okay, awesome. Thank you. Okay, so let's start with the homework question. Great. I'll start with the easier ones. Okay, so I'll kindly ask the people who are attending online just to see if they can see clearly that C or are not isomorphic. Can you guys see clearly? I can see clearly, but okay, thanks. Okay, so let's start. So, is there someone here? Yes. No, are you? You're in this class? Oh, okay. You just realized it? Oh, no, I'll just. Oh, okay. Okay. So, okay, great. So that C and R are not isomorphic. Okay, so first, suppose, how do we start? I think we did this example in class. Suppose that phi from C to R is a ring homomorphism. What question is this? Anybody has it on this?
I think so.
Question 7. Thank you. Okay. Great. So what can I say? Where does I go to? Where would I go to? If phi from C to R is a ring homomorphism, what relation does I satisfy? Then, of course, first of all, then phi of minus 1 is equal to -1. Agree with this, everyone? You agree with this? Then what is -1? -1 is I squared. Very full. Yeah.
It's like sit on the ground.
Yeah, you can say, but not in funny. Okay. Sorry about that. Okay. So so what can I say about phi of I squared? I mean, there is a spot. Okay, what can I say about phi of I squared? This is just phi of I times I, right? Agree or not? So good. Now, if phi is a ring homomorphism, how can I split this? How can I do with this? Yeah, phi of I. Phi of I times phi of I. So it's phi of I. It's phi of I is equal to -1. So phi of I squared is equal to -1. Now, to what ring does phi of I belong? Where does phi of I is?
R.
Phi of I is in R. But phi of I belongs to R. So can I find an element in R whose squared is -1? No, in R, can I find an element whose square is -1? Phi of I, and you can use phi of I squared is bigger or equal to 0 if you will. So no ring homomorphism from C to R. So C and R are not isomorphic. And if you can't find a homomorphism, then you can't find an isomorphism. Okay. Everyone in the audience, is it clear? Everyone online, is that clear? Everybody here, is that clear? Okay, it's clear. Should we do one more? We do one more like that. I mean, I think in the homework there is one more. Yeah, there's one more the same type. Should we do it, or I'll leave it as an let's we do it. Let's go over it. How many questions are there? 12?
Oh, yeah.
So I think this is the last question.
And it's 11.
11.
Well, there's 11 and 12. 11 is proofs of like two things are not isomorphic. And
Okay.
12 is proof that there's no ring homomorphism from something.
Z of I to Z mod B Z, right?
Yep. And then 11, it's Q of root P and then Q root Q.
Sure. So show that there is, well, so let P be a prime. Be congruent to 3 modulo 4. Show that there is no ring homomorphism from C of I to Z modulo Z. And what is Z of I? Maybe let me define Z of I. I think I defined in the question. These are all the elements of the form A plus IB, where A and B are integers. Okay? I defined this in the question. Now, you can convince yourself that this is a ring. Add A plus IB plus C plus ID, you get A plus C plus I times B plus D. Yeah.
Is I the symbol where I squared is minus 1?
Exactly. I squared is minus 1. Is the complex, is the imaginary. So I squared. Okay. Multiply two of them. You still get something with integer coefficients. Yeah.
Is that square bracket notation? Is that conjugacy class?
No. It's just a symbol. It's just a way to write something. Okay. This notation is a standard notation. We didn't see why we write it this way. But I hope in the next few lectures we see what this is. If I write Z of something or R of something or Q of something, we'll see what this was. Okay, great. Now, what's the idea here? Anyone can help? Anyone can? So where does I need to go to? If phi is a ring homomorphism from Z of I to Z mod BZ, I needs to be mapped to what? To an element whose square is minus 1. Now we know from before that if P is congruent to 3 mod 4, can I find the solution to x squared equal minus 1 in Z mod BZ? No, that's your question on the midterm,
Yeah.
right? So this is it basically. Yeah. Okay, so suppose phi from 0 to I is Z mod PZ is a ring homomorphism. Then phi of minus 1, it will just be the class of minus 1 mod P, right? Agree? Everybody, we agree so far? Yes or no? Because phi of 1 is 1, then phi of minus 1 is minus 1. Because the ring homomorphism properties. Well, this is phi of I squared is minus 1 mod P. Oh, what is phi of I squared? I can just take the square out. That's clear, right? I can write it as phi I times I. Okay, now since P is congruent to 3 mod 4, we know that x squared is congruent to 1 mod P has no solution. So can I find an element phi of I in Z mod PZ whose square is -1? If x squared congruent to 1 -1 mod P has no solution, can I find an element in Z mod P whose squared is -1? No, because P is congruent to 3 mod 4. Of course, if P is congruent to 1 mod 4, there's something else. Okay? But P is congruent to 3 mod 4, then I cannot find it. Is that clear so far? So phi of I squared is different than -1 P, hence there is no ring homomorphism from Z of I to Z mod PZ if P is congruent with 3. Okay, people attending online, any questions, please ask. We'll just wait. Okay, so far so good. Any questions on this?
So I don't understand how, well, firstly, x squared, we have to define that, or we just.
No, I mean, it's just that x is an unknown, so the equation x squared.
Square number,
Exactly.
And-
Exactly.
and-
But also x.
And
Or we know that x squared is different than -1 p for all. Sorry, just for all x and z mod p.
isn't I squared congruent to -1?
No, I squared is a number. I squared is a complex, is in Z of I, it's not here. Right? I squared. Oh, you mean I squared is congruent to -1 mod p? That's right. Yeah, I squared is -1. You mean, yeah, sure. -1 is congruent to -1 mod p.
What if x is I?
Well, x needs to be in Z mod PZ, right?
Oh,
Okay. So it's phi of I that is congruent.
and p is a prime number.
P is a prime number congruent to 3 modulo 4. Okay, we have seen that this equation, that x squared is always different than -1 if P is congruent to 3 mod 4.
Sorry, can you just re-explain why you know that 5 minus 1 and I squared equals?
Here, what is I squared equal to? -1, right? So 5 I squared is equal to 5 minus 1. Okay,
If this is, for example, let me explain why there's no solution.
well, I mean, I'll be clear. I'll be clear in these. I'll be clear in these. Yeah, but if the question is like that, you can say 2-3 words, and then you can explain why it's different. But usually, I'll make sure to ask maybe the first question: show that x squared congruent to -1 mod p has a solution. The second question will be: show that there is no ring homomorphism from Z of I to Z of p if p is congruent to 3 mod 4. But yes. Sure. So what? So it maps the so a homomorphism will map 1 to the identity of multiplication, which is 1, right? So 5 minus 1, because it's a ring homomorphism. It's just this property of ring homomorphism. I mean, it's the property of the group homomorphism, really. Right? You map the additive inverse to the additive inverse. Okay. Yeah, exactly, because that's the -1 is the additive inverse of 1. So it maps it to the additive inverse of 1 and the other. Okay? Yeah.
I'm repeating myself.
Sorry, I will just
Yeah.
sorry.
Oh, yeah, wasn't there some other condition for Bell-Markov theorem, like P doesn't divide by I squared or something like that?
P is congruent to 3 mod 4.
I know, but like for the part where like x squared is falling to -1 while P has no solutions. Wasn't there like a condition on P? P doesn't divide X squared or something like that. P doesn't.
Oh, P doesn't divide X, but of course I mean, the solution X squared is equal to -1, right? So of course P will not divide it.
Okay.
P will not divide 5i,
Okay.
right? Because if P divided, then 5i would be 0. Okay?
Okay.
See that?
Yeah.
Yeah. So X squared has no solution mod P, even if X is 0, right? For all X and Z mod P 0, because 0 squared is congruent to 0. It's not congruent to also. Okay?
Sorry, but
Yeah.
So the square brackets in this occasion
Is the equivalence class of 1 mod P. Okay. Is the residue class of -1. Okay. Great. Any questions? Do you know if I'm working with the subgroup that congruence or different? Cool. Matters. Okay. Is it clear? Okay. Great. Let's move on. People, let's see if someone people attending there. Very clear. Okay, thank you. Others? Questions? Awesome. I mean, now a good exercise, I mean, it's a tough exercise. Pick your favorite number, pick your favorite prime congruent to 1 mod 4. Let's say 5, and find all homomorphism from Z of I to Z mod 5Z. That's a nice exercise. Right? Because I can be mapped to 2. 2 squared is congruent to -1. Or it can be mapped to 3. So you can prove that every one of these is a homomorphism. I think we'll see that maybe next week. I hope to be able to study Z of I in details. So we'll prove good stuff using Z of I. Okay? So please know this, be comfortable with this A plus IB thing, A, B, and Z. This is one part of what you're gonna do. Okay? Great. Okay. I think this is okay. Let's move on now to another question. Let me see. Should we move to groups or stay in rings? Stay in rings. Let me see another question. Anybody has the printed version of the?
I could put it on my laptop for any place.
I mean, I have one. Yeah, it's a bit easier to find it, but thank you very much. So rings is from 7 to 12, right?
Yeah.
So the rings. We did 7 and we did 12, right? So what we have to do now is look at let's look at 9. Let's look at 10. 10 is that Q10. Show that it exists a ring homomorphism from Z mod and Z. Z mod and Z if and only if M plus N. Okay. Did anyone attempt this or? Yeah. It's not bad, is it? So I mean, one part should not be difficult. Let's see. So which one do I go first? If M, let's go, if there exists a ring homomorphism, then M divides it. Suppose, let's do it this way. Suppose, well, fill first. That Fi from G mod N Z to Z mod N Z is a ring homomorphism. Then M. Okay, that shouldn't be bad. Suppose, so what is phi of 1? What is phi of 0 mod n? What is that equal to? What is that equal to? Phi of 0 should be mapped to
0 mod n.
0 mod n. Very good. What is phi of 1? It's a ring homomorphism. So what's phi of 1? Very good. 1 mod n. Okay. Now what is phi of 1 plus 1? It's just by additivity. This is just 2 mod n. Agree or not? Great. Now, what is phi of n mod n? 1 plus 1 plus 1 plus 1 n times should still be equal to 1 plus 1 plus 1 plus 1 mod m n times. Agree or not? It should be this. So far, so good. Ask, don't hesitate to ask. So let's repeat once more. So what is phi of 1 plus phi of 1 n times? This is just n. Well, this is just phi of 1 plus phi of 1 n times. Agree? Now, what is phi of 1? This is just 1 mod m. 1 mod n n times. This is just n mod m. Agree? Now, what is phi of n mod n? I mean, n mod n is
0.
0, right? But phi of n mod n is just phi of 0 mod n. Right? Because n mod n is 0 mod n. Agree or not? The equivalence class of n modulo n is equal to the equivalence class of 0 modulo n. So phi of 0 mod n. Well, what is phi of 0 mod n?
It's
It's a 0 mod n. Awesome. So phi of n mod n is equal to n mod n, right? The class of n mod n is 0 mod n. Of course, you can do it in many other ways. Okay, there are other ways, but they're all equivalent. Okay. This is just yes.
How did you get from the penultimate to the last one?
Where? Here?
Yeah.
From here to here?
Yeah.
What is phi of n? This is n mod n.
Yeah.
Right? So n mod n, which is this one, is equal to 0 mod n. Okay. So n, there are many other ways to do it, but this is one. So n is congruent to 0 mod m. So m. Okay, this is. Okay, people attending online, do you guys have questions? Let's wait. Okay, is it clear? Everyone, is it clear? Okay. Of course, you can do it in many other ways. Okay, you can do it with groups. For example, you know that the order of phi of 1 divides the order of, so you know that the order, you can do it with groups, and you know. phi of 1 n divides the order of 1n. Okay, this is just the proof of that statement. What's the order of phi of 1n? This is just n divides the order of 1n, which is n. Okay. If you're comfortable with group homomorphisms, you can do that as well. Okay, it's very quick. But I'm kind of reproving the statements here. Okay, you see that? You see that? Okay. Should I do it the other way? Should I do it the other way or? Pardon me? No, I will not ask you to. You can choose the way. The other way is shorter. Is way shorter.
Oh, then yes.
Yeah, sure. I could do that. Anyway, it's Z mod n. Z mod n. Okay. I mean, I wrote it actually, but so the order. So well, phi of 1 mod n. Right? Agree? So the order of mod n divides order of 1 mod n. Okay, because phi is a group homomorphism. The order of phi of G divides the order of G. Okay, you can see that easily, right? So that's great. Since phi is a group homomorphism, then that's quicker. Okay. Awesome. I mean, it's a group homomorphism, and you're using the fact it's a ring homomorphism because it maps 1 to 1. Okay, great. Okay, now the other part is a bit more interesting. Anybody tried that? Anybody tried the second part? Yeah. Let's do it. So suppose m divides n. I want to define a homomorphism. You can do it in, well, I mean, you can do it in, well, I don't want to say phi from Z mod n D. Z mod n. Okay, let's think about the homomorphism. 0, where must it go to? If I want to construct such homomorphism, 0 must go to 0. 1 must go to 1 in the respective classes, right? Okay, so the equivalence class of X mod n must go to the equivalence class of X mod m. This is the only possibility that I have. Now I have to worry about something. What do I have to worry about? That is well defined. So let phi. So it sends the equivalence class of X mod n to the equivalence class of X mod m. Okay, so first we show phi is well defined. Phi is well defined. So if the equivalence class of X, what do I need to show? That if the equivalence class of X mod n is equal to the equivalence class of X mod n, then what do I need to show?
Then phi of
X mod n of X is equal to phi. Very good. Let's do that. So if X is congruent is equal to equivalence class of X mod n is equal to equivalence class of Y mod n, what can I say? This means that this implies that n divides x minus y, right? This is divides, I've used that symbol. Agree? Now I want to conclude that the equivalence class of x mod m is equal to the equivalence class of y mod m. Can I say that m divides x minus y?
Because m divides n.
M divides n. M divides n. Well, so this implies that m divides x minus y since m divides n. Agree? If m divides n and n divides x minus y, then m will divide x minus y. This implies that the equivalence class of x mod m is equal to the equivalence class of y mod m, which implies that phi of x mod n is equal to phi of y mod n. So my phi doesn't really depend on the representative. Okay. Now checking it's a ring homomorphism is straightforward now, right? I have phi is well defined. I can just check the three properties. How many three properties of ring homomorphisms? Is it clear so far? Is it good? Is it clear? People attending online, do you have questions? People attending online? No? Okay. Here? Any questions here? Okay, so I'll prove that phi is a ring homomorphism. Oops, I read that. Phi is a ring homomorphism. What is phi of x plus y? Well, sorry. 5. And you know this is it. Or less obviously now, it's just phi x plus y, and then which is just okay. Okay, now what do I have to check? I have to check that phi of 1 mod n by definition is just 1 mod n, that's good. And then phi of x mod n, y mod n. Okay. People online, no questions? Is that clear? So phi is a ring homomorphism. Any questions on this? So the key is well defined, right? The key that is well defined. Now, once you have it, it's well defined, then checking it is straightforward. Yes.
When you went from the residue class xm and ym plus
Here.
ym, and then you
Here.
went straight to phi, yeah, but
Here.
not to the last, yeah,
Here to here.
yeah.
By definition.
Isn't it?
By definition of phi.
No, I know, but isn't it the other way around? Is it? And swap the ends and the m's from my.
No, I'm applying phi to z mod n z, right? So phi of something mod n will give you something mod n. Okay, so phi of something mod n will give you something mod n.
Works both ways.
No, not both ways. What do you mean?
If
Yeah,
phi
what?
of something mod n gives you something mod n.
That's it. Phi of something mod n.
Oh,
gives me
okay,
something
yeah,
mod
yeah,
n.
yeah.
Okay. No problem. Okay, are we good here? We good? Great. Now, question. Oops, oh, I shouldn't have erased that. Were you guys writing? Are you guys done or not? Yeah, okay, great. Everybody done? Yeah. Questions, anyone? Still good, okay. Yeah, go ahead. Ring homomorphism, it respects the multiplication. It respects the addition. And the multiplicative identity gets back to the one. Okay? Okay. Now show. And I mean this a ring homomorphism. What did I pick? Z4 to Z2 plus Z2? Is that it? Yeah. Or does there exist? Right? Does there exist? Does there exist a ring homomorphism from Z4 to Z2 Z plus Z2? What do you think the answer is?
Yes.
What do you think the answer is?
Yeah.
Given the previous question, just find the homomorphism from Z4 to Z2, and then just replicate it, right? So what would your ring homomorphism be? So from Z4 to Z12. Okay, 0 mod 4. Where would it go? It will go to 0 mod 2, 0 mod 2. Agreed? 1 mod 4, where would it go? 1 mod 2, 1 mod 2. 2 mod 4, 0 mod 2, 0 mod 2. Because it's 1 plus 1, right? And 3 mod 4. We just go to 1 mod 2. Yeah.
I understand the first two, but why does 2 mod 4 go to 0 mod 4?
Oh, so what's 1 plus 1?
Oh, it's mod 4. What?
Mod 2. So 1 plus 1 mod 4 is 2 mod 4. 1 plus 1 mod 2 is 0. You should add the images.
1 plus 1 mod 4 is 2.
Yeah, mod 4, it's 2 mod 4. And then 1 mod 2 plus 1 mod 2 gives you 0 mod 2. Right? Phi of 2 should be phi of 1 plus phi of 1.
Oh, you're adding the ones?
Exactly. You're adding all of it. Exactly.
What?
Because it's a group homomorphism. It respects the addition. Is that clear?
I thought you were going from like 2 mod 4, like representing that in mod 2.
Exactly. Yeah. So 2 mod 4, what's 2 mod 4 mod 2? 0 mod 2, right?
Yeah. And what question is this? Sorry.
Okay.
8.
Wait,
8.
please. Yeah. Yes.
Why is 3 mod 4 went to 1 mod 2? Or 1 mod 2?
Sure. 3 is 2 plus 1.
Ah.
Okay. Or it's 3 times 1. Really, what you're doing here is taking the homomorphism from the previous question and just adding another replica to it. So what you're doing is just phi of x 4. You just x mod 2. X mod 2. This is well defined and a group homomorphism. Okay.
Also make one where like 1 and 3 are 1, 0, 4, 0.
So the identity in the ring, the multiplicative identity, needs to go to the multiplicative identity in the other ring. What's the multiplicative identity in the other ring? 1, 1. You're not doing a group homomorphism. If you were doing a group homomorphism, then you have more freedom. But here this is imposed. that the identity, the multiplicative identity here, must go to the multiplicative identity. Okay, once these two are chosen, then everything else is chosen. Because, yeah, is that clear? Any questions? Okay. Just wrote it down. And it's well defined and respects the product. It's really from the previous question. Okay, so what you do is that you find the homomorphism. So what you, Mhm. Well, it's not that they're repeaters. You really have no other choice. Okay, you really have no other choice for this one. And this is a well-defined homomorphism because really it's this one. Okay.
Do we have to prove in this question, like prove well-defined, prove,
Um,
or can we say like
technically you should do that. Okay. But you can say, look at the
by
previous
previous?
question. Is it previous or after? Look at the question after. Yes. Okay. And then you can do that. Okay. So it's more or less. Okay, look at the question after. This is just the ring homomorphism from Z4 to Z2. But I just put another. You see that? Everybody, you see that? Yes.
The also about those equals.
Z mod for Z cross Z mod for Z to Z mod to Z cross Z mod. So what you have to do, you have to map 1, 1 to 1, 1, right?
What do you do with like
Exactly.
1, 2?
That's and you have to map 0, 0 to 0, 0.
Can you do like AB maps to AB?
AB maps to AB mod to, yeah, that works. But is that, yeah, I think that works, yeah. AB mod 4, but I'm trying to find all of them, right? This is it.
Yeah.
Here, I think you don't have many, right? You don't have many. But if you want to find all of them, so AB mod 4, B mod 4, and you reduce it mod 2, this gives you a ring homomorphism. Right? I think so, yeah. So 1 gets back to 1. But are they all of them? I just have to double check. Because all you need to find is where does 0, 1 go to? And where does 1, 0 go to? Once you have 0, 1 and 1, 0. So no, once you have 0, 1, and you know where 1, 1 goes to, then you have everything else.
Yeah,
Okay.
because then you can just
You can just
build them by adding them.
Exactly, exactly. Okay, so I'll have to double check. 0, 1. Okay, I mean, yeah, it's a good question. I use all homomorphisms. It's just a calculation. It will just come up nicely. I mean, you know, you can find the possibility where does 0, 1 go to. For example, the phi of 0, 1. What is 0, 1 squared? This is just 0, 1, right? So it should be phi of 0, 1. Okay. Now you look at the element in Z mod 2, Z cross Z mod 2, who equal to their squares. Okay. But that's all the element. That doesn't help. That doesn't help because you have 0, 1, 0, 0. So that doesn't help. Maybe, yeah, maybe you have many. Okay. Yeah, maybe you have many. So this is the main idea. I mean, the order, yeah, okay. Great. Now, do you have more ring questions or we're done?
Yeah.
9. Okay.
9 and 11.
9 and
11.
11. Okay. Anyone help me with 9? What is
9
9?
is R and S commutative rings, and you have to show that the ideal of R times S is the Cartesian product of the ideals.
Okay, so show that if what letter did I use? K is an ideal of R cross S.
Then
K
equals
is equal to
ij.
I times J, where I is an ideal of R and J is an ideal of S. Okay, so let R and S. Okay. An ideal of R cross S. Show that K is I plus K, where I is an ideal of R and J is an ideal. Okay.
Isn't a commutative ring field
No.
with something else?
No, a commutative ring generalizes fields. Right? I mean, a field is a particular case of commutative ring. A field is a commutative ring where every non-zero element has a multiplicative inverse. Okay?
So like where A, B is 0, either A or B.
No, it doesn't integral domain.
Ah.
Okay, yeah, you have to the definitions are you have many definitions. Yeah, so a field is like where you have for any non-zero A, you have a B, of course that is non-zero, such as AB is equal to 1. R, for example, is a field. Because for any non-zero real number, you can find a real number such as A times your real number is 1. So take 1 over x, for example, times x. If x is non-zero, you get 1. But Z is not a field. Z is not a field because you cannot find an inverse for 1/2. Very good question. Someone asked a very good question. Is it possible to build a ring isomorphism from Z mod 4Z to Z mod 2Z cross Z mod 2Z? I think not, but just want to make sure. Your thought is correct. Because if you can build a ring isomorphism from Z mod 4Z to Z mod 2Z cross Z mod 2Z, then the two additive groups would be isomorphic. Right? So if you have a ring isomorphism between Z mod 4 and Z2 cross Z2, then you have an isomorphism of groups between them. But Z mod 4Z is a cyclic group where one is generated by 1. So it has an element of order 4. But Z mod 2 cross Z mod 2 doesn't have any element of order 4. It's not a cyclic group. Very good question. Very good question. Is that clear? Did I answer your question? So if you have two rings and the additive groups are not isomorphic, then you cannot find a ring isomorphism between them. Because if they're isomorphic as rings, then they're isomorphic as groups. Okay? That's a very, very good question. But the converse is not true. So you can find two rings that the additive groups are isomorphic, but they're not isomorphic as rings.
Because of the other condition.
Because of the other conditions, exactly. We will see a bit more of these finite. I mean, we will work with finite stuff. But yeah. Okay, great. So great. Let's yeah, okay, thanks. Yeah, okay, so let's prove this. Now, that's not an easy question. That's not an easy question, but we don't have many candidates for I and J, right? Once you have something like that, what are your possible candidates for I and J, really? Well, I don't say we don't have many, but the obvious ones, take I is R and R, such that there exists S and S, such that RS plus. Okay, so what you really take is that you have the K. So the ideal K contains elements of the form RS, right? Agree? your ideal K is an ideal of R cross S. Agree or not? Yeah. So it contains elements, pairs of the form RS, right? What I'm saying, just pick all the R's alone. And let this be a candidate for I. Now, what is a good candidate for J? Someone help me? What's a good candidate for J? It's the set of all S's in S such that there exist R in R, such that R, well, in RS belongs to K. Okay, maybe the notation is not the best here because I should have switched R and S, but it doesn't matter. Great. Now, if I show I is an ideal, then you can show that J is an ideal as well, right? It's the same idea. Agree or not?
Mhm.
If I show I is an ideal, by the same argument, J will be an ideal. Okay, let's show this. Let's show that let's show it. Okay, I is an ideal of R. Is an ideal of R. Great. Now, what do I need to do? First, I need to show that I is a subgroup of R. So does 0 belong to I? Does 0 R belong to I?
Yeah.
Does 0 R belong to I? So can you find an element in S such that 0 and this element belongs to K?
Yeah.
0. Why is that? Anyone can help me?
Because 0, 0 has to be.
0, 0 has to be in K. 0 R, 0 S belongs to K. So 0 R belongs to I. Because K is an ideal. Agree or not? So far, so good. Any question? Any questions? Yeah,
Can you just say what you just said again?
sure. Here?
Yeah.
Okay. You want to show that I is an ideal. So your first thing is to show that I is a subgroup. Okay, now what's the first part to show that I is a subgroup? That contains the additive identity, right? Now, does 0 R belong to I? So what is the question you ask yourself? Okay. Can I find an element S in S such that 0 R and S belongs to K? And the answer is yes, because 0 R 0 S belongs to K. Is that clear? Okay. So 0 R belongs to. Great. Now suppose that R1, R2 belong to I. We need to show that R1 plus R2 belongs to I. Agree or not? Okay, now R1 belongs to I. What does it imply? It implies that there exists S1 in S such that R1 S1 belongs to K. R2 belongs to I implies there exists S2 in S such that R2 S2 belongs to K. Agree or not? Now, can I say that? Okay, K is an ideal. I'll keep this here. I'll raise the question. People attending online, do you guys have questions? No? No questions. Okay. So R2 belongs to I, there exists. Okay. Now, can I say that R1 plus R2 belongs to I or not? Can you find an element in S such that R1 plus R2 little s belongs to K or not? What? Yeah, what is that element?
S1 plus S2.
Exactly. And why is that?
Because
K is n.
I wrote it down somewhere. I forget.
Yeah, because K is an ideal,
Right. Yeah.
right? Since K is an ideal, of R cross S, and R1 S1 plus R2 S2 is equal to R1 plus R2 S1 plus S2 belongs to K. Of course, forgive me for not writing R and S, addition in R, addition in S. I think from now on I will drop that. It's understood that every addition is happening in the respective ring. Okay, so R1 plus R2 S1 plus S2 belongs to K. This means that R1 plus R2 belongs to K.
Why?
Belongs to I, sorry, thank you. So far, so good. Great. Yeah.
Right. R is additive on the S and S additive on the R.
Well, what do you mean? S is additive under R. No, this is the addition in S, right? This is the addition.
Okay,
Okay, so it's not the same addition, but I won't write it every time. Because it's yeah. Because if I write it every time, I'll forget it. Okay, so I'll just prefer not to write it for once. But okay,
double check with.
yeah, no, that's good. But I mean, it's good that sometimes it's addition is not as obvious, but allow me to erase it because I will not write it every time. Okay, yeah. So I need to check it's a subgroup first. And then I still need to check that R1, R2 is in S, but for any R2, not for R2 in I, right? So what you need to check that 0 is in R, right? You need to check 0 is in I. And if R1 and R2 are in I, then R1 plus R2 are in I, right? Because it's a subgroup under addition. You need to check it's a subgroup of R under addition. So that's first. And then you need to check that R times R1 is in I, if R1 is in I and R is in R. Okay? And that gives you that it's the additive inverse is there, right? Because if you let R be -1, you win. Okay, you don't need to check -1 separately. If you check R times R1 for any R in R, then that's what you get. Yeah.
So how did we know it was under addition?
R is a ring is always a group under addition. There is no ring that is a group under multiplication except the 0 ring. Okay. When I talk about group under multiplication, I need to take the units of the ring. 0 does not have any multiplicative inverse. Unless it's a 0 ring, which we're gonna throw away for that. We're gonna throw away, we're not gonna consider the 0 ring. Okay, always R is a group under addition. Okay. Okay, let's finish this. R1 plus R2 is in I, then what? Then
Yeah,
what did I need? Yeah.
We need
Okay.
inverse, right?
Pardon me?
Now we need like the.
Yeah, that's the minus one.
Yeah.
Okay, but let's think about that. If I've managed to prove that if R is in R and R1 is in I, if I manage to prove that R times R1 is in I,
Then
I can, if I let R is equal to -1, then I get the additive inverse. You agree or not?
Yeah.
So, I mean, we need to show something. We need to show that if R is in R and R1 is in I, we need to show that R1 belongs to I. Agree or not?
So it's like instead of doing the third condition,
We just do.
we can just go to the other condition of ideal, and
Exactly.
it will imply that it's a.
Yeah, exactly. We see that? Yeah.
The mark says only addition.
Yes, but the definition of ideal is a subgroup under addition, and it's closed under multiplication in R. So if you multiply an element of R by an element R1 in I, then you still land in I.
And if you add them, you still land in it.
Exactly. Cool. It's strong than it's stronger than having to multiply two elements in I landing in I, because you need to any element in R you multiply by R1 you get in I. This is the stronger property.
Stronger meaning.
Strong. I mean, it's not enough to show that if R1 R2, sure, that's true. If both belong to I, then their product will belong to I. But you need a stronger one. If R is in R and R2 is in I, the product of R. Okay? Great. Could I erase this or should I keep the definition? I keep the definition. I can erase it? Erase it?
Yeah.
Yeah. Okay. Now let R be in R. question is I want to find R. What do I want to do? I want to show that R1 belongs to I. Now I know that R1 S1 belongs to I, right? I know that R1 S1, sorry, belongs to K. Sorry. Okay. The goal is to show that R1 belongs to I. Now, if R1 S1 belongs to K, what can I say? How can I let R into play?
Then R.
Yep.
If you take RS.
If I take
Like RS. Belongs to K since it's
RS times R1 S1. Yeah, okay. So you get R1 times SS1 belongs to K because it's an ideal. Very good. Yeah.
Sorry, could you just explain again why we need to show that R1 is an R?
Yeah, definition of an ideal.
Yeah.
Okay. Definition of an ideal. If R is an R and I is and R1 is an I, then R1 is an I. So yeah, very good. So you can take RS. Now you know you can give a value for S as well, right? You put S equal 1, for example. Okay, you can, but yeah, sure. Let's put then RS belongs to K. So far so good, agreed? I can put S equal 1. And you can put S equal 0. Doesn't matter, right? Then for all S, okay, then for all, let's use another word. For all V and S, I don't want to. Okay, VS1. I just don't want to use S. Okay, very good. Hence, R1. Yeah.
How do you know that VS1 is in S if S is in a group under multiplication?
If S is in a group under multiplication.
It's not a group under multiplication, so then
No, I mean, so you know that R1 S1 belongs to K, right? So if you multiply it by anything in R cross S, you still land in K.
right.
Agree?
Okay.
Multiply this by RV.
Yep.
Put any value of V you want. You put V equals 0, V equal 1, anything. You still land in K.
Okay, so it's because it's in K that you know that VS1 is an S.
And K is an ideal. So no, V must be nice. Right?
Yeah, because it's in K.
Okay. Is that
Right,
clear?
yeah.
Okay, but now that we've shown that I and J are ideals of R and S,
Yes.
we still need to show that like IJ is ideal of RS, right?
I cross J
Yeah, I cross J, sorry.
is an ideal of
Of R cross S.
R cross S. Great. Now, if you show that K is I cross J, you win immediately.
Yeah, that's what I
Yeah.
mean. That's what we.
Exactly. Okay. So far so good. Yeah.
But you know how you put V and S? Why didn't you swap S1 for V1?
No, because R1 S1 belongs to K.
Oh, okay.
Okay. Yeah. So now I is an ideal. Hence I is an ideal. Agreed? You agree? Yeah. Okay. So you can find VS1 RR1 belongs to K. Agree or not? So this means that RR1 belongs to I. You found an element. Okay. Hence, I is an ideal. R, what can I say as well? Similarly, J is an ideal of S. J is an ideal of S. Similarly. Yeah. I guess the similarly should go here, but I don't have no space. So similarly, J is an ideal of S. Okay, great. Now what do I have to prove? I have to prove that K is I cross J. Need to show. that K is equal to I cross J. Yeah.
But if you take any RS in K, then by definition, like by construction, R is in I and then S is in J. Like,
Yeah, exactly.
so that's why we built the I in J that way.
Exactly. So let RS belongs to K. I mean, I'll just use let AB belong to K. Right? Then clearly A is in A is in I, and B is in J. By definition. Agree or not?
Sorry.
Yeah, okay. You appeared in the camera. I'll have to blur you.
Sorry.
Yeah. Is that good or not?
But is it enough? Or do you have to show the other side?
Of course. You have to show the other side. Let A be, then A is in I and B is in J. So K is contained in I cross J. That's clear. Now the other side. Other side. Wait a second. Let A belong to K, then A belongs to I, and B belongs to J. Right. Okay. Is that, yeah, that's, I think that's good, right? But also the other way. Yeah. Now let xy belongs to I plus J. Then there exists S in S such that xs belongs to K. And there exists R in R such that what? Ry belongs to K. Now, how do I finish this?
Multiple.
Anyone can help here. How do I finish this? I need to show that xy belongs to K, right? That's what I need to show. Right? Xy belongs to I cross J. I need to show that xy belongs to K. How do I finish this? Yeah.
Well, isn't this I equals J is 8K? You say well, and XY is 8K, so I say is 8K.
Not necessarily. It's not necessarily true. You know that xs is in K.
But we don't know this. Okay.
You know that xy is in I cross J, right? You want to show that it belongs in K. Okay, let's do something. Now we'll use the fact that K is an ideal. Now x s belongs in K. And that's as simple. It's not very, that's a bit, those are not very hard statements. We just have to write down the correct elements. So xs belongs in K. Okay, now can you find a way where I get to this? I need to get here. I want to get here. I want to show that x0 belongs to K. Now I know I can multiply by elements in R cross S and still land in K. Agree? By what element in R cross S I need to multiply xs to get x0? What's an element that would do it?
0.
1, 0. So 1, 0. Hence 1R 0S xs belongs to K. K, then R cross S ideal. So x0 belongs to K. Agree or not? Any questions here? Yeah. R contained R cross S is an ideal. Agree? So far so good? Now I can do the same thing. If I multiply 0, 1 by Ry, Similarly, what? 0R and what? And 1s times ry belongs to k. So the 0y belongs to k. I mean x0s. Here I have to. Agreed? So far so good? So far so good. Now if x0 belongs to k and 0y belongs to k, I can add them and get xy belongs to k. Okay, what time is it?
7:15.
7:50?
15, man.
Oh, 13. Okay, 15. Okay. Hey, someone told me I won't finish in 2 hours. So I think they're right. Yeah. Hence, x0 plus 0y belongs to k. So xy belongs to. Hence, I cross j containing k. Therefore, k is equal to I cross j. Okay. Great. So far, so good. Any questions here? Yeah.
Sorry, I don't know how 0, 1 could be.
I mean, you know, if it's an ideal of R cross S, then if you multiply an element in K by any element in R cross S, you still land in K.
Yeah.
Now, multiply by 1, 0, you get that x0 will belong to K. Multiply the other element by 0, 1, you get that 0y belongs to K. Now, remember that our goal is to show that xy belongs to K. Now, how do you get xy from x0 and 0y? You add them together.
So you just used it to prove this multiplication in K.
No, I use it to prove that if xy is here, then xy is in K. Now, how do I do that? I did that by proving that x0 is in K and that 0y is in K. If you manage to prove both of these two, you can add them up and you get that xy belongs to K. Okay?
Well, there's an element in.
No, you mean here. You're talking about this one.
Yeah.
Yeah, so here you're making your choice. You're just making a choice to make the proof works. Okay, it's not you can use 2, 0, for example, but that might not work, right? That might not give you what you need.
It's 1, 0 and 0, 1 always work.
Well, in this proof, yes. In this proof, that's because that's what you need. If you use 2, 0, you get 2x and 0, but that might not give you what you need.
How do you know what you do?
Well, you need that xy belongs to k. That's what you need. Okay, so if you use 2 and 0, may not work. Okay? Yeah.
Did you just prove that I cross J is an ideal of R cross S? Like you've done it that way.
Sure, even if you prove it's an ideal, then y is it equal to k?
Okay.
Yeah, well, two ideals are not necessarily equal.
What could I just like be the? Because it didn't define it.
Did I say show that? What does the question say?
Let
Show that
be
k.
an ideal
Yeah.
of R cross S. Show that-
Exactly. So you have to show that these two sets are equal. It's not enough to show that I cross J is an ideal. Okay? Is it clear? Of course, if you have the product of two ideals, then you can show it's an ideal. Okay, yeah. Yeah. That's always true. Yeah. And then any ideal in the product ring is of this form. That's not true for subgroups. Yeah, if you have a product of two groups, then it's not the case that any subgroup is a product of two subgroups. Okay? Yeah, you see that? For example, take ZP cross ZP and take diagonal 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Well, let's pick Z3 cross Z3. 0, 0, 1, 1, 2, 2. That's a subgroup of Z3 cross Z3. But that's not the product of any two elements. Okay? Great. Okay, now we have one more in rings. Should we do it or we should move on to groups?
We should do it.
We should do it? Okay. Okay, who wants to move to groups? Who wants to move to groups? Should we move to groups? Okay, who wants to stay in rings? Yeah, but I mean, there are many who did not raise their hands. So please, all of you, raise your hand. Who wants to move to groups? Who wants to stay in rings? Okay, so the rings win. I mean, groups, I think we can just do the ones that are a bit problematic. Okay, great. And just what is the? I think it's Q root P and Q root Q are not isomorphic if P and Q are distinct prime numbers.
Yeah.
Okay. Did you guys see in our analysis classes that root P is irrational? Did you see that root P over Q is irrational if P and Q are distinct primes?
Yeah.
Did you see that?
Yeah.
Would you believe me if I said so? If you, this is not hard to prove. So, for example, if P and Q are different prime numbers, then root P over Q is an irrational number.
Yeah.
Would you believe me if I said this? Okay, just prove it by the same way you prove that root P is irrational. How do you prove that root P is irrational? Say, okay, root P is M over N, where M and N are co-prime, right? And then you say P squared is M over N. Sorry, so P is M squared over N squared, and you get that P N squared is equal to M squared. So P will divide M squared, so P will divide N. You plug that back in, you say M is equal to KP, and then you get that P will divide N, right? So P will divide both, contradicting the fact that they're co-prime. Right? Is that how you do it?
Yeah.
Yeah. No, no, so you don't need to put that. And the same way you do root P over Q is irrational. You say root P over Q is M over N, P and Q are distinct. And then you say that, let's see, P over Q is M squared over N squared. So N squared times P is equal to Q times M squared. So Q will divide. Oh, shoot, okay. Okay, so that's, I mean, you know, root P over Q is M over N. So P over Q is M squared over N squared. So N squared P is equal to M squared Q. Okay, everybody, just a second. So Q will divide N squared times P, right? Q and P are distinct prime. So Q will divide N squared. Okay, Q will divide N squared. So Q will divide N. Okay, so Q will divide N. You can say N is K times Q. So you get K squared Q squared P is equal to M squared Q. Cancel one Q out, you get K squared Q P is equal to M squared. So Q will divide M. Same argument, okay? Same argument that will lead to Q, that will lead to M and N are not co-prime. Is that clear, or should I write this down? It's clear. It's fine. It's good. Okay. Okay. So show that Q root P is not isomorphic. Q, P Q distinct primes. Okay, now let's prove that.
Yeah.
Suppose that phi Q root P root Q root Q. By the way, look at the additive groups of these two. Those two rings, you cannot find, we are not able to find the ring homomorphism. But look at the groups of these two elements. The additive groups are isomorphic. The additive groups are just Q squared, basically. Right? You're just adding A and the B. So, okay, anyways, we can. These are vector spaces over Q. And if you have seen that before. Yeah, okay, yeah. Okay, so that's it. These are two-dimensional vector spaces over Q. So I think you'll see this next term, or maybe we'll do a bit of vector spaces this term.
No,
A little bit. Pardon me?
would have been fine.
We'll see. I mean, it's
You write it?
pardon me?
Already
Did you write the
done.
final?
I wrote it, yeah. You'll see. I know. You will see. I saw already. Okay, so suppose that Q root P to Q root Q is a ring homomorphism. Now, again, what's the key here? What should phi root P squared satisfy? Or what is phi of P? Phi of P, what should it be equal to?
P file. Yeah.
P phi of 1, which is? What is phi of 1? Phi of 1 is equal to 1. Agree or not? So what is phi of P? What is phi of P? P, right? Because it's phi of 1, 1, 1, 1, 1 plus 1 plus 1 plus 1 plus 1 P times. Okay, now what's phi of root P? So this is phi of root P squared is equal to P. Agree or not? So this is just phi of Is that good? So far so good? Same way. Great. Now all I have to do is to show that the equation x squared is equal to P, that you don't have any elements in Q root Q whose squared is equal to P. That's what you need to show. Right? Yeah.
And you just go like phi of root P is equal to root P, and then just show that root P doesn't exist in the.
Yeah, okay. So phi of root P is equal to root P. Now what is root P really?
Because if you have root P and you want it to be like A plus B root Q, then you know that you can't do it with the A because it's irrational.
Okay.
And if
Very
you
good.
have the B, well, it still doesn't work because B still has to be a rational
Sure.
number. And if
Sure.
you could multiply both, then it wouldn't
But
work.
let's pay attention. That phi of root P squared is not necessarily root P. It's phi of root P squared is P.
Yeah.
But that doesn't mean that phi of root P is root P. It could be root P or minus root P.
Yeah, but even if it were
Sure.
minus root P, we
Yeah,
would still
but
get
you have to pay attention to this.
Yeah,
It's
yeah,
the same thing. But root P here, okay? Is that clear?
yeah.
So we have to pay attention when you square root equations.
Yeah, because you have plus or minus.
Plus or minus. But so what you can show is that you have no solution to x squared equal P, or equivalently that the real solution of x squared equal P, which is root P, does not belong to Q root Q. Now, both of these are subfields of R. Those are subrings of R.
Yeah.
Now, I don't want to use that. I just want to do it in a more general way. I just want to show that you don't have any element whose squared is P, Q root Q, because in general, it's going to be a more general. It's a more general way. You will be using that.
It's subring.
It's subring of R. You're not using that. Okay, root P really is the square root of P in R. Okay, but that works. But you have to pay attention that it's plus or minus root P here.
Yeah.
And then if root P doesn't belong, then minus root P doesn't. Okay. So now let phi of root P is A plus B root Q for some A, B, and Q. Okay? Now what is A plus B root Q squared? This is equal to B. This is just A squared plus B squared Q plus 2AB root Q is equal to B. Right? So far, so good. Let me put the rational part. Well, thank you. Now I claim, well, this is rational. Agree? This belongs to Q. Right? A and B belongs to Q. P is an integer, so boom, all of these belong to Q. Now, when will this one belong to Q? Root Q doesn't belong to Q. So 2AB belongs to Q. Root Q belongs to Q if and only if what? Is 5 root 2 belongs to Q? Does 5 root 2 belongs to Q?
No.
Does 3 root 2 belongs to Q? If you want to multiply something that is not in Q and land in Q, what should that something be?
you have to get rid of the root in some sense. So you would need a root Q there.
So you need to.
You need a root Q.
No, but AB are in Q. Right? AB are in Q.
So either you get this like a zero,
Exactly. So
or
AB
you
must be 0. If and only if is equal to 0, because A and B are in Q, right? You agree with this or not? Yeah? Yeah.
But how is, if root Q is not
In Q.
how is 2AC?
Oh, because this is in Q. 2AB root Q is equal to this, and this is in Q.
Oh, fair enough.
Okay. Now, when does 2AB root Q belong to Q? If and only if AB is equal to 0, because A and B are rational numbers. Okay, now when does AB equal 0? If A is equal to 0, so let's write this. So we must have hence AB is equal to 0, and what do we have? A squared plus BQ squared plus B squared Q is equal to B. Right? So if A is 0, what can I say? I can say that B squared Q is equal to P. Agree? This means that what? This means that root P over Q yes. Okay, let's work with positive numbers. We're working with an R, so we can use the full power of R. That means that root P over Q is the absolute value of B. Agree or not? Root P over Q is root of B squared, which is the absolute value of B. This means this one belongs to Q. Agree. Contradiction, because P over Q, root P over Q is irrational. Contradiction. Doesn't belong to Q. Okay, now, if B is equal to 0, what do I get? If B is equal to 0, if B is equal to 0, very good, then A squared is equal to P, which implies that root P is equal to the absolute value of A belongs to Q. Prediction. Hence, no ring homomorphism from Q to P to Q. Okay, rings are done. Let's see if the people. Let's see if the people. What? Anyways, let's see if the people online have questions. Do you guys have questions online? Maybe we'll wait 30 seconds. Any questions? Okay, now we move on to groups. Maybe I'll have to stay 15, 20 more minutes, but yeah.
Could we maybe start with question 4? If that's okay.
Another question 4 is.
It's like the one, the third question.
Order 93.
It was on the.
Yeah.
Yeah. So that could be nice.
So I mean, before I need the question before, right? I think. Okay, I'll. Okay, so
Let GG group of order 96.
yes, but I think for that I need the question before.
Oh, the previous one?
Yes,
Okay.
Q3, yeah, Q3. Okay, great. Okay, are we good with rings? Are we good with rings? Q3. Okay, so Q3. Debate group. Oh, some people have questions. Theodore, does the session end at 8 for those in the chat. No, I mean you I'll stay. Don't worry, I'll stay. I mean it won't end at 8. I don't think I'll be able to finish by 8, but yeah. Unless I mean I can leave by 8, I don't have a problem. Unless you want me to stay, I'll stay. But if you want me to leave, I don't mind. So let G be a group and P be a prime dividing G. Let G be a finite group and P be a prime dividing the size of G. Show that the following are equivalent. Oh, yeah, I forgot something. Let P be a Sylow P subgroup. Yeah, okay. Let P be a Sylow P subgroup of G. Show the following are equivalent. What are these? P is a normal subgroup of G. And 2, P is the only Sylow P subgroup of G. Okay. Great. Let's prove that. Which way do you want to start? I think I said at some point that the proofs should be very short.
Yeah.
They should not, and they're very short, right?
Yeah.
Yeah. Anybody tried those? They're very short, right? Yeah. Okay. So let's do 1 implies 2. 1 implies 2. So suppose that P is a normal subgroup of G, then P is the only Sylow P subgroup of G. So let K be a Sylow P subgroup of G. By Sylow's second theorem, what could I say? Conjugate. By Sylow's second theorem, there exists G and G such that K is GP G inverse. Now, if P is normal in G, so K is equal to GP G inverse. When is that equal to? If P is normal, GP G inverse will be equal to P. Okay? Hence, any Sylow P subgroup is equal to P. Okay, is that clear? Is that clear? Great. Let's prove 2 implies 1. Again, should not be very long. Implies 1. Let X be in G. Suppose P is the only Sylow P subgroup. Then XP X inverse has the same size as P. We agree? As a subgroup. We don't want to make it 3 lines, so of G and XP X inverse has size P. So XP X inverse is a Sylow P subgroup of G. Now P is the only Sylow subgroup of G, right? P is the only G. So XP X inverse is equal to P, hence P is normal. Okay, that you don't need Sylow theorems for this, right? You just need that they have the same size. So if I tell you a group has only one subgroup of order 10, then this subgroup is normal by the same order. Okay?
Can we say
all G in G, G inverse will be equal to P.
Because all the conjugates.
Yes, you can use that. You can say that. You can say that all the conjugate are equal to P, but this is more general. Okay, so all the conjugates will be equal to P. So what I want to say, if P is normal, no. If P is the only Sylow P subgroup, yeah, sure, you can do, but then you don't need Sylow theorems for this, right? It's if I tell you that a group G has only one group of order 10, one subgroup of order 10, then this subgroup is normal by the same way. Okay? But yeah, I think you can use that. I think you can use that. Let's see. You can use that. Yeah, I mean you can use Sylow theorems, but you don't need it. Okay, great. Awesome. You can say that okay, that KBS, like KBS Sylow P subgroup, then K is equal to P. And it's all the conjugates of P. Yeah, okay. Sure. Yeah, you can use that. But this doesn't you don't need the Sylow theorems. Okay, great. Now this one is done. Let's do Q4. Q4 is it's weird because again you have two ways. A implies B. I think many people didn't have trouble. Most of you don't have trouble with that. And that's longer and more involved than B implies A. So B implies A is short. A implies B is a bit long. So what did I say? Let G, what was that, Q4? Let G be a group of order 96. Show that the following are equivalent. 1, G has no, this is what I said, has no normal subgroup. Size 32, order 32, 2. There exists a surjective. Group homomorphism. First group homomorphism. Morphism from G. That's 3. Which one? Let's do 2 implies 1 first, okay?
Yes.
Let's do 2 implies 1 first. Then show you some does. Some does if you use the right theorems. Okay, great. So let's do 2 implies 1. First isomorphism theorem. So let's draw from G to S3 be a surjective group morphism. Okay. Yeah. Let n be equal to curve rho. For simplicity, I'm not gonna write curve rho everywhere. Then G mod n is isomorphic to S3. Agree or not? First isomorphism theorem. You agree or not? Now S3, how many subgroups of order 2 does S3 have?
2.
Order 2? How many subgroups of order 2 does S3 have? 3. Right? S3 has 3 subgroups of order 2. We agree? So G mod n, how many subgroups of order 2 does G mod n have? If it's isomorphic to S3.
Same.
Agree or not? S3 has G mod n. Well, G mod n has 3 subgroups of order 2. Since G mod n is isomorphic to S3. Okay? We agree or not? S3, how many subgroups of order 2 does S3 have? Are we good with this or not? You want me to write the subgroups down or that's okay? Should I write it down? Yeah, so I mean, what are the subgroups of order 3 in S3? So just 1, the identity, and 1, 2. The identity, and 1, 3. And the identity, and 2, 3. These are the only subgroups of order 3 of order 2 in S3. You have 3 of them. Yes, sir.
Why are we looking at the subgroups of order 2
Yeah,
and not the 3, not order 3?
so that's the thing. Okay. Okay, you agree with this? G mod n has how many subgroups of order 2? 3, sorry. 3 has 3 subgroups of order 2. Okay, I'll just erase that. Let's call them H1, H1, H2, H3. Yeah.
Sorry, why can't you put 1, 2, 1, and 1, 3 together? 1, 2.
But this is not a subgroup. Yeah, you have to be close in a multiplication.
Yeah, there is.
You have to, yeah, exactly. So if you have 1, 2, and 1, 3 in a subgroup together, then it's the whole group. Yes, and it's a whole group. Yeah. Okay, H1, H2, and H3. Hence, phi n inverse of H1, phi n inverse of H2, phi n inverse of H3 are subgroups of G of order. What is the order of these subgroups? They're just H1. H1, H2, and H3 have the same size, right? Which is 2 size. Times the size of n, which is 2 times the size of kernel of rho, right? Agree? Agree or not? Yeah. What is pi? Pi n is just G mod n. That's times G. G. Okay. Now, of order 2 times n, what is the size of the kernel of rho? 96 over the size of the kernel must give me 6, right? G mod n is isomorphic to S3. So the size of G divided by the size of n must give me 6. Agree or not? Yeah. So what is the size of n? 16. 16. So it's 2 times 32. Oh, wait a minute. How many Sylow 2 subgroups do I have? A group of size 32 is a Sylow 2 subgroups, right? Because 96 is 32 times 3. How many Sylow 2 subgroups do I have? 16. At least 3. So the size is 32.
Where'd the 2 come from?
The size of H1, H2, H3.
Right, okay.
Homework 7, question 1, right? Yeah. This is homework 7, question 1. Homework 7, question 1. Yeah.
Where did 16 come from?
Oh, 16. So G mod n being divided by n at size 6, right? So 96 divided by 6 is n 16. Okay. So how many subgroups of order 32 I have? Let's say at least 3 for now. Okay, you have at least 3. I mean, you have exactly 3. But you have at least 3 subgroups of order 32. Now, subgroups of order 32 are exactly Sylow 2 subgroup, are the Sylow 2 subgroups. So you have more than one Sylow 2 subgroups, hence none of them is normal. Okay? Is that clear? Yeah. So subgroups of order 32. Hence what? Hence. G has more than one Sylow 2 subgroup. What is the size of a Sylow 2 subgroup in that case? 32, right? G96 is the 5 times 3. So how many subgroups? You have more than one subgroup of order 32. You have at least 3 of them. I mean, you have exactly 3 in that case, but you have at least 3 of them. So you have more than one. So none of them is normal. So G has no normal Sylow subgroup. So G has no This is a bit too much details, but that's okay. There's no normal subgroups. Or because if it were normal, it would be unique by the previous one. Exactly. Are we good? Is that clear? Is that clear? Is there any group action involved here? Nothing really sophisticated, but it seems that it gave some trouble. Maybe I guess, yeah. The A implies B is harder. 1 implies 2 is harder, right? 1 implies 2 is more involved. You have a group action, you have a kernel, and you have to look at that, and you have to show it's surjective. Right? 1 implies 2 is more involved than this. It's less intuitive, maybe, yeah, yes. It's less intuitive. So basically, you have to maybe, yeah, okay. So maybe you want to show how do I get subgroups of order 32, basically. So basically, you have to think that I have the kernel of size 16. How can I construct? Yeah, also, yeah, I agree. Less intuitive, but yeah, But I mean, yeah.
Is the kernel the largest?
No. Why is the largest? What do you mean the largest normal subgroup?
Largest.
G is the largest normal subgroup. Okay. G is the largest normal subgroup.
Largest that's contained in A.
That's contained in H. What is H?
The
Sylow 2 subgroup.
Yeah.
In that case, I think it is.
Because there's index 2, so I think it has to be.
You mean no, but no, it's the largest normal subgroup in H.
Yeah, but it
Yeah,
has
yeah.
something bigger than
No, but basically you can have another one of the same index, but not contained in each other.
But then it won't be bigger, it'll be the same size.
It will be the same size, but not contained. Right? Like they won't be contained in each other. Now, when you say the bigger normal subgroup means that any other subgroup is contained. If you mean in size, then yeah. But H is normal in H, right?
Yeah.
But I think so. What if you mean that the intersection of the conjugates of the Sylow 2 subgroups is the kernel in that case? I think I believe so. Yeah. In that case, I would believe so. I think so. I mean, I just have to double check. So, I mean, if n is normal, let's see. N is contained in one of them, right? So n is contained in the 3 of them. Right? Now you can show that the intersection has size 60. And then yes, n would be the normal subgroup. I think n would be the only normal subgroup of size 60. But I'll have to double check. Okay, I'm just saying where is that. But I think in that case it will be the only normal subgroup of size 60, which is the intersection of the conjugates of P. In that case, if P is not normal. Yeah. Okay. But yeah, we don't need to prove that. Okay, we don't need to prove that. Because I mean n is contained in P, right? In one of them. So n will be contained in all the conjugates of P because n is normal. Okay, so and all the conjugates of P have size 2, have size 16. If you take the intersection of the conjugates, it has size 16. And if n has size 16, then I think that the only normal subgroup of size 16 in that case, the n, will be the intersection of the conjugate. I think so, yeah. I mean, don't take my word. I have to sit down and write it. Okay, yeah.
Have we done 1 to 2 or are we?
No, we're just starting with. I think 1 to 2 is 1 to 2, okay? Number 1. Okay, so I'll just finish this one. 1 to 2, is it okay? Or should I do it?
It's okay.
Should I do it?
Yes.
Yeah, okay, let's do 1 to 2. 1 to 2 is a bit more involved, but I think you're more used to that. Fourth question. Okay. Now G acts on the set G mod P. Oh, so okay, sorry. I mean, you know that. Let P be a Sylow 2 subgroup. Sylow 2 subgroup of G. Let P be a Sylow 2 subgroup of G. P has size 32, and by assumption, P is not normal in G. Okay, P is not normal in G, then what? Let G act. And G might be. How do you let G act? So you say G star and XP. GXP. This needs this action induces a homomorphism rho from G to S3 or sim G mod B, which is isomorphic to S3, whose kernel is N, the intersection XP inverse is contained in P, right? Now N is normal because N is a kernel. N is normal in G because N is a kernel. Is that clear? Should I write this down that N is normal? Since N that I named the homomorphism since N is equal to kernel. So N is different than P. Since P is not normal. Agree or not? Agree or not? So far, so good?
Mm.
Yeah. Hence, G mod N is isomorphic with a subgroup of S3 and G mod N is strictly bigger than the index of P, which is 3, since N is contained but not equal to P, it's contained in G, and P has index 3. Agree? So what can I say about, yeah? So N is contained in, where here? G index N is strictly bigger than G index P. Okay? Since N is contained in P, which is contained in G, and G index P is equal to 3. N is contained in P, but different than P. Okay? So what can I say about the image? So G, the index of N in G. The size of S3 is 6, and G, the index of N in G, is bigger than 3. So what can I say? So Gn is 6. So rho of G has size 6. Now, what is the only subgroup of S3 that has size 6? It's 3. S3. So rho of G. So rho is surjective. Okay. I'll do one more. I think, the dihedral group, the one of S4. Is that clear, everyone? Is that clear? Yeah.
Wasn't this supposed to be 3 lines?
No, not this one. The other,
But that wasn't 3.
the other one I detailed them.
Oh, okay.
But the other one is this one. This is why I said this one is more involved. This one you have an action and you have to count and you have to, right? The other one is take 3 subgroups of J mod N of order 2. That's are the pullback images. You know the inverse image of the projection. Boom. This one is a bit. This one is not boom. This one you have to write it down. Okay. Great. I'll do maybe 2 more exercises. I'll do the S4 one. So let's see until we get kicked out of the room. Oops, started. Okay. Great. Okay, I'll just. Okay, any questions so far? Any questions on this? Any requests? Question 1, and we'll do that.
Question 5.
Question 5. What's question 5?
S4.
That's 4. Okay. Anybody has any requests? Okay, let me see the people in the chat. Okay. No problem. Okay, so folks, any questions? No problem. Any questions? So let's do the S4 one. The S4 one is a question I like a lot. I've given it like maybe I've done it like 2 times in class, 1 time in the previous homework and 1 time this homework. You know, I think it's at the door. Thank you very much.
Yeah.
Okay, let's do the S4 question. Oh, which one? Yeah, but do you have the question written? So I can, oh, thank you. Okay. Okay, so let's S4. Guys, please. Everyone, yeah. Okay. Let S4 be the symmetric. Plus 4 letters. Show that S4 had the subgroup H with of order 8 of order 8 by listing its elements explicitly. And I say show that H is not normal, right? Or is H normal? I don't know. Show that H is not normal. It's 4. And then I ask you, by the way, there is the discussion board on the, yeah, okay, so please make use of it, okay? Write down questions there. I've let you like post anonymously. So you can post anonymous like questions. I can't see your name, so please post questions, but again, avoid questions of the type, is this gonna be on the final, and we have that, and we have that, okay? So please avoid questions of that type and ask questions of the material. I will happily answer you.
What if it's like material that you think we should know?
You can come and ask me. You can ask me first.
Like that's to not know.
Yeah, I mean, you know, I think I'm clear on what you should know, what you shouldn't. Okay, so it's okay, B, what is B? Find all the subgroups of order 8 in S4 and write them down. Did I ask you to write them down explicitly?
Yes.
And write them down. C. Use A and B to find surjective homomorphism. Is that I think I remember them. Yeah, homomorphism from G from S4. Are these the questions?
It also
Yeah,
says
but-
to write down the kernel.
Write down the kernel explicitly. Very good. Right. Now, it's kernel explicitly. I don't know why I wrote that. I'll have to erase it soon, but work here now. Okay, now I want a subgroup of order 8 in S4. What's a good way to find this? Of course, don't try to multiply elements and find your own groups. You will never you will never finish. What is a good group of order 8 in S4? What is it, everyone? The dihedral group of 4 elements. Of course, I have to represent it in permutations. What do you suggest? How do I find them in permutations? How do I write down a dihedral group in S4?
Like label one.
I write down a square and I label it 1, 2, 4. Okay. One, 2, 3, 4. Okay. Now I write down the symmetries of that square. How many symmetries do I have? Everybody, how many symmetries do I have?
8.
8, right? So, not how many reflections? 4.
Oh.
How many rotations? 4. So how many symmetries in total? 8. Symmetries isn't used for vertical for reflections or no, symmetries can mean both, right?
Yeah.
Yeah, symmetries can mean both. But anyways, vertical, horizontal. I have a diagonal D1. I have a diagonal D2. Let's write them down. H identity. What's the rotation? What's the main rotation by 90 degree here? What does it do? Someone help me out? Yeah.
1, 2, 3.
1, 2, 3, 4. A 4 cycle. Very good. Then what's that squared? When I square that, what do I get? 1, 3, 2, 4. And then in our cube is 1, 4, 3, 2. Then I have V. What is V? There's 1. You flip 1 and 2 and 3 and 4, right? And then you have D1. What's D1? Well, you have H. H, you flip 1, 4, and 2, 3. You have D1, it's 2, 4. And you have D3 sorry, you have D2 is 1, right? That's it. Okay, I've done that in class, did I not?
Mhm.
Yeah, I've done that in class. Okay, great. Now what I ask, show them what? Show that
It's
8 is
normal.
not normal.
It's not normal.
So what do you suggest doing?
You relabel it.
You could just
Yeah, sure, but why does it show it's not normal? By Sylow's theorem, very good. That's one way of doing it. So if you relabel the square, you find another subgroup of order 8. You know that subgroups of order 8 are Sylow 2 subgroups. So if there are more than one, they're not normal. Very good. Or another way.
can we just do like you pick another one that's not it and you multiply and you see that it doesn't.
Exactly. So we can do both. So both are good. Both are good. I'll use your trick for another. Yeah, I'll use your trick for another one. Okay. So, but if I'll try to work more generally. Okay. So more generally, let's pick an element. So I mean, in that case, any element that is not in H will do the job. In general, it's not true, but in that case, it's true. So we want to find a G in S4, so that G inverse is not equal to H. That's what you want to do. What's your suggestion here?
1, 2.
1, 2. So your first guess in general should be an element that is not in H. It may work, it may not work. In this case, it will work. Okay, so what do you want to do? 1, 2, H. So I mean, here it's also more or less obvious as well that it's not normal. Why is that? If it were normal, it would contain all 4 cycles. It will contain the entire conjugacy class, right? It would contain all transpositions if it were normal. So you have many ways of doing it. Which one do you prefer? Shortest one. Okay. I mean, let's try to not use many theorems. Okay, you could do it here. I mean, you guys see the argument. If it were normal, you know that normal subgroups are a union of conjugacy classes. So If it were and two elements